Hey folks, let's work through your practice test number 3. I'm going to do a video solution for most of the items on the practice test. And the first one is you were asked to solve this exponential equation. So here's how I'd begin the problem. I would rewrite 1/3 as 3 to the negative first power. And that's still raised to the 6x plus 5. And I'd rewrite 9 as a 3 squared. And that's still raised to the x minus 4. And now I'd use an old property of exponents that when you have an exponent raised to an exponent, you can multiply those two together to get 3 to the negative 6x minus 5. And this exponent times that exponent would give me 3 to the 2x minus 8. And now I'm going to use what I call the preservation of equality. Remember the preservation of equality? When the bases are the same and you have one exponential expression equaling another exponential expression, and the bases are the same, the only way this can be a true statement is if the exponents are equal. So if I tag the problem on up here and I set the exponents equal to each other, negative 6x minus 5 equals a 2x minus 8, all I have to do now is just solve for x. And I'll probably start off by adding 6x to both sides. And then I would add 8 to both sides. And then finally divide both sides by 8. Gives me the solution to this exponential equation. X is equal to 3/8. And that's all there is for number 1. Okay, here in number 2, I told you that the rabbit population in a certain forested area is growing at about 8% monthly. In September, there were 290 rabbits, and the population can be modeled by this function. T is the number of months. Determine how many rabbits we should expect by next September. Okay, now see, everything here is in terms of month. It's growing at a rate of 8% monthly, so that tells us that our independent variable T is number of months. So if we want to know how many rabbits we're going to have next September, that's 12 months from now. So all we have to do is evaluate this function at 12. 12 months from now would be next September. So we evaluate this function at 12. And so we put a 12 in for the T. And yeah, we crank this through the calculator. I'm so happy we have a calculator here. So you crank this through the calculator, you get something close to 752.5. Okay, since we're talking about rabbits, let's not have any decimal or fractional parts of a rabbit cruising around in this forest. So I would simply go to the next whole number, and I would say next September we're expecting 753 rabbits to be in this forested area. And that's all there is to number 2. Okay, here in number 3, I asked you to solve this exponential equation. So it's kind of similar to number 1. First thing I noticed is on the left-hand side, my base is e, and on the right-hand side, I'm going to rewrite 1 over e to the 4th as a base of e. And that's just using an old property of exponents that 1 over e to the 4th can be rewritten as e to the negative 4th. And then on the right-hand side, if I multiply those exponents together, I get e to the negative 4x minus 12. And again, here comes our preservation of equality. Bases are the same. In order for this to be a true statement, these exponents have to be equal. So if I tag it on over here, and I set the exponents equal to each other, well, now all I have to do is solve for x. And I'll start off by adding 4x to both sides. So I get a 5x minus 3 is negative 12. Add 3 to both sides. So I get 5x is negative 9. Then divide both sides by 5. And I get x equals negative 9/5. And that's the solution for number 3. Okay, here in number 4, I tell you that an investor has put $3,000 into a savings account that accumulates interest at a rate of 1.3% compounded continuously. I didn't copy this down correctly. So the amount in the account after t years is given by this function. A of t equals 3,000 e to the 0.013t. And see, I had 4 parts here. Part A, does the function model exponential growth or exponential decay? Okay, folks, remember when the base is e, if the base is e and the exponent's positive, it's exponential growth. If the base is e and the exponent's negative, it's exponential decay. So since the base is e, the exponent's positive, my answer to part A is that it's exponential growth. I'm not going to write that up here. Part A, the answer is exponential growth. Now part B says evaluate A of 0, and what does that represent? Well, so for part B, I evaluate A of 0, so I put a 0 in for the t's, and I can do this one without my calculator, because this exponent will be 0. E to the 0 is 1, so 3,000 times 1 is 3,000. Now what does that represent? Well, t is time in years. So if I'm putting 0 in for t, that's telling me my initial amount I invested, the initial amount that was deposited. So quite simply, A of 0 being 3,000, that just tells me that initially $3,000 was invested into this account, which we knew from the words of the problem. Okay, now part C, you're supposed to solve the equation A of t equals 6,000, find the exact answer algebraically, and then use your calculator to get a decimal approximation. So in part C, A of t is 6,000. So this is 6,000. Put 6,000 in for A of t, and this is what we're trying to solve. Well, divide both sides by 3,000, and you get 2 is equal to e to the 0.013t. And then from here, I'm just going to go back to, how exponential equations and logarithmic equations are the same thing. That if you have an equation, if you have an exponential equation, you should be able to write it as a logarithmic equation. Or if you have a logarithmic equation, you can write it as an exponential equation. Excuse me. Well, here's an exponential equation. As a log equation, this is just the natural log of 2 is equal to 0.013t. So that's just taking the exponential equation and writing it as a logarithmic equation. To solve for t, I would divide both sides by 0.013. So the natural log of 2 over 0.013, that is t. Folks, that is the exact solution. You were asked to do 2 things here. Get the exact solution, and then use your calculator to get a decimal approximation. So this is exact, and when I use my calculator and do the natural log of 2 divided by 0.013, I get the approximation. T is approximately 53.32. Okay, now part D. What does our solution to this equation, A of t equals 6,000, what does that represent? Well, what it represents, notice we put 6,000 in for A of t. That's twice the amount we invested. That's twice the 3,000. So all this solution represents is that it's going to take about 53.32 years for the money to double. It's going to take about 53.32 years for the money, the initial 3,000 that was invested, to grow to 6,000. That's it for number 4. Hey, before we do number 6, let's quickly talk about number 5. Number 5, I asked you to evaluate the expression e to the natural log of 13. That's just simply going to be 13. So that was a friendly one. Number 6, determine the domain of this logarithmic function, and let's write the solution in interval notation. Folks, we have a log function. We got to remember those bad things in function land. Remember, you can't divide by 0. You can't have a negative number appear under an even indexed radical. And here for logarithms, you cannot take the log of 0 or a negative number. You cannot take the log of 0 or a negative number. So there's a lot going on here. First, the first thing I note, the number 4 cannot be in the domain. 4 can't be in the domain because that would cause 0 in the denominator. You're not allowed to have 0 in the denominator. So we know 4 is not in the domain. The second thing I notice, x cannot be negative 5. If x is negative 5, then the whole fraction here is 0. You can't take the log of 0. Okay, so we can't take the log of 0. We can't take the log of a negative number. So that brings me to the third thing that I have to analyze. The third thing. When is x plus 5 over x minus 4, when is that a negative number? Well, in the very first section, section 1.9, in a video I made there, and something that you learned in 1.9, what we saw was how to solve rational inequalities. And that's really what this is, but let's review that real quick. Remember, to solve a rational inequality, remember I kind of put my completely factored numerator and completely factored denominator, I kind of put them there on the side, and then I find negative 5 on the number line and 4. And if you remember, I made dashed lines, and then I put a 0 here, because x plus 5 is 0 at negative 5. And I put a 0 here, because x minus 4 is 0 at 4. And then remember what we did is we picked numbers and tested them. Picked numbers in each of these 3 intervals and tested them. So for example, I would pick negative 6. I know negative 6 is definitely in the interval negative infinity to negative 5. When I put negative 6 in here for x, I get a negative number. When I put negative 6 in here for x, I get a negative number. And then remember, we move to the next interval, negative 5 to 4. Pick any number that's in that interval, like the number 1 is in there. If you put 1 in here for x, x plus 5 is positive. If you put 1 in here for x, 1 minus 4, well, that's negative. And then remember, you move to the third interval, 4 to infinity. Pick any number that's in that interval, like 5. Put 5 in here for x, you'd get a positive number. Put 5 in here for x, you'd get a positive number. And then remember our process. We're talking about x plus 5 divided by x minus 4. On this interval, x plus 5 divided by x minus 4, that would be a negative divided by a negative. Well, negative divided by a negative is positive. On this interval, negative 5 to 4, it would be a positive divided by a negative. Well, positive divided by a negative is negative. And then finally out here, it's a positive divided by a positive, which is positive. And I think we can finally write our answer. The domain is, remember, you can't take the log of a negative number, but you can't take the log of 0. Well, on the interval negative infinity to negative 5, x plus 5 over x minus 4, x plus 5 over x minus 4 would be positive. We can take the log of a positive number. So negative infinity to negative 5, that's part of the domain. Parenthesis around negative 5 because negative 5 would make this 0. You can't take the log of 0. Out here, x plus 5 over x minus 4 is also positive. So that too is part of the domain. And again, 4 is not in the domain because you can't divide by 0. So that's the answer to the domain of the function log x plus 5 over x minus 4. Hopefully that makes sense, and that's it for number 6. All right, hey, here in number 7, I asked you to use the properties of logarithms to expand this expression as much as possible. So this is making sure we know all of our properties and laws of logarithms. When you have the natural log of e to the 5th over 8, there's a law of logarithm that says you can rewrite this as a subtraction. So that'd be natural log of e to the 5th minus the natural log of 8. Okay, now we have a property that tells us that the natural log of e to the 5th immediately simplifies to 5. And that's it. That's as far as I can go on expanding that log expression using properties of logarithms. So that's your answer to number 7. All right, hey, number 8, I ask you to use the properties of logarithms to condense this logarithmic expression. And make sure that you write the expression as a single logarithm that has a coefficient of 1. So we're going to condense this down as much as possible. Oh boy, I guess the first thing I would notice is I have an addition in here. So there's a law of logarithms that says I could rewrite this addition statement as multiplication. So let me take care of that. That would be 1/5 log base 4 of x times y. And I can't do anything here yet. Okay, next, there's a law of logarithms that says these coefficients that are out here. There's a law of logarithms. Those coefficients were originally in an exponent position. So I'll go ahead and put those back in the exponent position. So that gives me log base 4 of xy to the 1/5 power minus log base 4 of x plus 1 to the 5th power. So I took both of those and put them back in their exponent position. Okay, next, I don't like this 1/5 exponent, so I'm going to use an old property of exponents and just rewrite this as log base 4 5th root of xy. Okay, now finally, we have a log minus a log. There's a law of logarithms that says when you have a log minus a log, you could rewrite that as a division. So I would get log base 4 5th root of xy over x plus 1 to the 5th power. So I've taken this beastie and I've condensed it down to a single logarithmic expression, and the coefficient is a 1. So that's what's happening in number 8, and hopefully you got it, and hopefully so far you know everything's making sense. Okay, here in number 9, I asked you to solve the logarithmic equation. If there's no solution, you have to say there's no solution. Here I'm going to use that preservation of equality again, the preservation of equality that says when you have one log expression equaling another log expression, as long as the bases are the same, the only way this log expression can equal that log expression is if the 2x plus 5 is equal to the 3x minus 8. So that's preservation of equality. Now to solve this, I would subtract 2x from both sides, and then add 8 to both sides, and I get x is equal to 13. That's it for number 9. Hey folks, here in number 10, I ask you to solve each exponential equation and then round your answers to 4 decimal places. So the first one, you have 2 to the x equals 7. I'm going to take the log of both sides of that equation. I can't rewrite 7 as 2 to some power very easily. So whenever I'm trying to solve, it's in the exponent position. I kind of think logarithms. And specifically, I'm going to take the natural log of both sides. So I have the natural log of 2 to the x equals the natural log of 7. And then that property, or that law of logarithms, allows me to take this exponent and move it out front. And then divide both sides by the natural log of 2. And that would be my exact solution. Natural log 7 divided by natural log of 2. But to have the answer to 4 decimal places, I crank this through my calculator, and I get x is about 2.8074. So that's it for part A. Part B, 10e to the 1.2x equals 20. I have one step I'm going to do first. I'm going to divide both sides of the equation by 10. So that gives me e to the 1.2x is equal to 2. Folks, I can take this exponential equation, and you should be able to do this as well, and just immediately rewrite it as a logarithmic equation. In other words, 1.2x is equal to the natural log of 2. That's just taking exponential equation and rewriting it as a logarithmic equation. So if I divide both sides of this equation by 1.2, there is the exact solution to the equation. X equals natural log of 2 divided by 1.2. But again, I wanted you to get a decimal approximation and round it to 4 decimal places. So when I crank this through my calculator, I get 0.5776. So that's it for number 10. All right, here number 11, I gave you a couple of logarithmic equations, and the directions were very straightforward. Solve each logarithmic equation. So when I look at this first logarithmic equation, what jumps out at me is the preservation of equality. I have a log expression equaling a log expression. The bases are the same, so the only way this can be true is if x squared minus 21 is equal to 4x. Well, this is just an old quadratic equation now that we're left with solving. You know, I would subtract 4x from both sides, and then I hope this factors. I always try to solve a quadratic equation first by factoring. If it doesn't factor, then I use quadratic formula. But let's see. I think it factors to x minus 7 times x plus 3. Set each factor equal to 0, and we get x is 7, or x is negative 3. Okay, people, remember, we've got to check our answers here. We've got to at least make a reasonability check. You can't take the log of a negative number. So let's look at x equals 7. If I put 7 back in here for x, well, 7 squared is 49. 49 minus 21 is 28. Okay, that's good. 7 here, 4 times 7 is 28. That's good. I have log base 3 of 28 equals log base 3 of 28. That makes sense, so this checks. But more importantly, I wasn't finding the log of a negative number. Let's look at x equals negative 3. Immediately I notice if I put negative 3 in here for x, 4 times negative 3 is negative 12. I can't take the log of negative 12. I don't care what the base is. You can't do the log of a negative number. So that means this solution, remember the big fancy name for it? It's an extraneous solution. And remember, extraneous, that's a fancy way of just saying it's bogus. So this equation only has one solution, x equals 7. Now we kind of break this off here. Let's look at part B. Log base 2 of x minus 2 plus log base 2 of x plus 2 equals 5. Hey, I'm going to start off using a law of logarithms. Addition, that means I could put it back together as a multiplication. Log base 2 of x minus 2 times x plus 2 equals 5. Heck, we know what x minus 2 times x plus 2 is. That's x squared minus 4. And now I'm going to take this logarithmic equation and I'm going to rewrite it as an exponential equation. You're kind of noticing how that's an important skill, being able to go back and forth from logarithmic equations to exponential equations. So the exponential equation for here would be 2 to the 5th equals x squared minus 4. That's 32 equals x squared minus 4. That's a friendly quadratic equation to solve. Personally, I'd add 4 to both sides. And then I'd take the square root of both sides to get x is 6 or x is negative 6. But again, check. Make sure they both are reasonable. If I put 6 in here for x, 6 minus 2 is a positive 4. 6 plus 2 is a positive 8. I'm not worried. But if I put the negative 6 in here, negative 6 minus 2 is negative 8. I can't take the log of a negative number. Since I can't take the log of a negative number, that would be an extraneous solution. So the only solution to part B is x equals 6. So hopefully that makes sense. Hopefully you're feeling pretty good about the test. But there's one more to look at, number 12. All right, hey, here number 12. Sarah has $2,000 to invest at 4.75% interest. It says for parts A and B, round your answer to 3 decimal places. Part A, how long will it take before she has $3,200 if the interest is compounded monthly? Part B, how long will it take for her to have $3,200 if the interest is compounded continuously? So that means for part A, I need this compound interest formula. For part B, I need this compound interest formula. Remember, this is the compound interest formula for continuous compounding. This is all the other types of compounding. So let's see if I can substitute in what we know. We know what Sarah's starting with. She has $2,000 to invest, so that's her principal. We want to know how long it's going to take before she has $3,200. So $3,200 is the A, and $2,000 is the P, her principal. We know the rate is 4.75%, so as a decimal, that's 0.475. Interest in part A, it's compounded monthly, so N is 12, and T, that's what we're trying to find. We're trying to find T. My first step, divide both sides by 2,000, and I get a 1.6 equals, and I'm just going to continue to write this down. 1 plus 0.0475 divided by 12 to the 12t. Now, and I'm going to keep writing this down. Now I'm going to take the log, or the natural log of both sides. I'm trying to solve for the variable that's in the exponent position. So natural log, or log, is my friend. So if I take the natural log of both sides, that will then allow me to use a property of logarithms and take that exponent and move it out front. So the natural log of 1.6 equals 12t natural log 1 plus 0.0475 divided by 12. Now I'm going to divide both sides of this equation by 12 natural log 1 plus 0.0475 divided by 12. That way I'll get t by itself. So I have this mess, folks. The natural log of 1.6 divided by 12 times the natural log of 1 plus 0.0475 divided by 12. That's equal to t. And now's when I fire up the calculator. And I crank all this junk through the calculator. And when I crank all this through the calculator, I get 9.914. Or to answer the question more specifically, about 9.914 years. It takes about 9.914 years for the money to grow to $3,200. Now you may be wondering, why didn't I crank this through my calculator earlier just to make it, get a number here? I really can't, because when I crank this through my calculator at this step, the 1 plus 0.0475 divided by 12, I got a big, long, ugly looking decimal. I can't round that. If I round that too early, I'll be slightly off here. And I want to save all rounding to the very end. So part A, it's about 9.914 years. Part B, see everything, all the numbers are still the same. A is still 3,200. P is still 2,000. The rate is still 4.75%. And my first step is still the same. Divide both sides by 2,000. Now where it gets a little bit different and a little friendlier than part A is I can write a logarithmic equation now for this exponential equation. This exponential equation is the same thing as saying the natural log of 1.6 is equal to 0.0475t. And then I can divide both sides by the 0.0475. And while that's my exact solution for t, when I crank it through the calculator, I get about 9.895. And again, that's years. It's about 9.895 years. So if Sarah invested into the account where the interest is compounded continuously, it takes about 9.895 years for her $2,000 to grow to $3,200. Where it's compounded monthly, it takes about 9.914 years. Intuitively, that makes sense. Compounding continuously grows just a little bit quicker. All right, folks, well, that's it for practice test 3. That's it for number 12. We've done them all. So hopefully you're feeling really good and confident. You're going to go knock test 3 out of the park. Good luck, and thanks for watching.